Welcome. Good morning on Wednesday. Um, Sorry for I didn't get to get another lecture done on Monday, but let's hope we get a lot done today. Okay, so let me just share a slide so that you can see. Okay. Okay. Um, Before we start, any questions about the logic, right? We have last time we have learned on the topic of predicate logic, right? So like we make the sentences that are not propositions and make them into a propositions which can each statement or each sentence can now have a truth value, right? Either it's true or false, right? So I think we are right here. Okay, I think we stop. Um, I think we stop here before we start.
อาจารย์ลืมเปิดไมค์หรือเปล่าคะ
โอเคครับเดี๋ยวนะอ่า
หนูได้ยินอาจารย์ปกตินะคะ
โอเคครับ can you hear เริ่มเปิดเสียงโอเคครับคุณอัชรานันท์โอเค um that can happen sometime โอเคครับlet's continue from what we had last time. Okay, so last time we discussed about two sentences, which is the let me just go back a little bit. um, the first one is the universal quantifier statement, right? The universal quantifier statement is the statement that have the universal quantifier, right? So you can see the a symbol that for all like this in the sentence. That's what we call a universal quantifier statement or a universal statement. And then you also have the existential statement where you have the symbol that exists, okay, or existential quantifier. And this one just uh, it's similar to the universal quantifier statement, but the truth value is a little bit different, right? As we discussed it, for universal statement, it will be true if every x in the domain of D is true, and it will be false when at least one of the x in the domain of D is false. Right? For this one, it's really true if at least one of x in the domain of D is true, but it will be false if all the x are false, right? I think we've seen some example. We see how you can translate from English sentence into a quantifier statement. We can see that this is for universal statement, and this is the existential statement, right? And I think we reach here, okay? So imagine if you add a negation to the universal statement, okay? For example, if you have a for all statements, a universal statement for all x in the domain of D, Q of x, okay? When you add the negation to it, what you get is for all will switch to the exists, and then you have to factor in the negation. So Q of x will become negation of Q of x, right? So basically, it's, if you have a negation outside, add to the universal statement, you can have the x negation of Q of x. Okay, it's easy, right? Looking at the symbol, it's quite easy. For example, another one, negation of the existential statement. Okay, so you have the exists x in the set of D such that K of x. Okay, the negation will become for all x, negation of Q of x. Okay, so the opposite, right? If you have for all, you switch to for some. If you have for some, you switch to for all. Okay. So just to summarize, okay, if you have negation of for all x, p of x, you have there exists x, negation of p of x. If you have negation of the exists x, p of x, you have for all x, negation of p of x. Okay. It's quite easy looking at the symbol, but let's see if you can do it with the actual English sentence. Okay. So let's see example 18. Okay. Can you find the negation of the following statements? Okay. The first one, for all prime numbers p is odd. Okay. For all prime numbers p is odd. What's the negation of this statement? Okay, for all prime number p is odd. So what's the negation of this statement? So this one, is it for all prime p is not odd? Is that the negation of this one, or for all prime p is, I should say, for some prime p is odd? So what's the negation of this one? For all prime numbers p is odd. Okay. So if you think of the sentence directly to find the negation of this one, it might be, I mean, it might be not obvious. Okay, it might be not that easy. Okay, but if you translate it into a symbol, for example, if I translate this sentence for all prime numbers p is odd, and then I write it as for all p, okay, in the set of p, let's say this is the prime set of all prime numbers, okay, and then for all p in the set of prime numbers q, let's say q is a statement that is p is odd. Okay, so what we have is negation of for all p in the set of p q, right? So for all p in the set of prime number q, so the negation of this one is, well, as we know that for all we switch to for some, and then q we switch to negation of q, right? So we have there exists p is not prime number, right? So there exists prime number p, which p is not odd. Okay, right? That's the negation of the of the sentence, right? Any question for this one? Okay, let's see another one. There exists a triangle T such that the sum of the angles of T equal to 200. Okay, what is the negation of this sentence? There exists a triangle T such that the sum of the angles of T equal to 200. There exists a triangle T such that the sum of angle of T equal to 200. What's the negation of this one? So, I mean, if you try to translate directly to find the negation of it directly, it might be very difficult. But if you translate into a symbol first, for example, this one I can translate into, because it's the exists. So I'm using the exists quantifier. So it's say that a triangle T. So I use the symbol T. Okay, and then I use the let's say the set of T, which is the set of all triangle, and then I use a symbol R to represent the sum of all triangle equal to 200. Okay, so what I have is that there exists T in the set of T R. Okay, and then I put negation outside. So for this one, we can have the negation of this one is for all T in the set of big capital T, negation of R. Okay, so this is what it means that for all, I have, I should write down. Yes, so this means that for all triangle T, okay, the sum of all angle of T is not equal to 200. Sorry, right? Because it is for all triangle T, the sum of all triangles of T is not equal to 200, right? So the opposite. Okay. Any questions so far? Nope. Okay. The last one, the last topic of this one is that you can have more than one quantifier. Okay. You can have for all, for some, two for all, two for some. Okay. Depend on how many variables in there. Okay. For example, you can have something like this. For all x in the set of R positive, the x is y in the set of R positive, P of xy. Okay. You can have something like for all for some, and the order of for all for some is significant. Okay, you cannot just swap it. For example, let's see these examples. For example, let's say that if you have a symbol P of xy, means that x likes y. Okay, so this symbol for all x, the x is y, P of xy means for every person, there is someone they like, right? For all x, there is someone that x like, let's say y. However, if you write it like this, there exists y for all x, P of xy. This one will mean that there is someone whom everyone likes. Okay, whom everyone likes. Is this the same? Is this symbols? Is this the same? For every person, there is someone they like, and there is one person whom everyone likes. Are they the same? Well, they're not the same, right? I can give you like really simple example. Let's say that in this situation, there is only 3 persons in the class. Let's say A and B and C, okay? So the first sentence say, for every person, there is someone they like. So you can say that, oh, for this sentence to be true, you can say, oh, A likes, let's say A likes B, and then B likes, let's say C, and then say C likes, well, let's see like B, okay, right? This one, this in this situation, this statement is true, right? For every person, there is someone they like, right? Yeah, A like B, B like C, C like B. However, for the second situation, for there is someone whom everyone likes, this for this sentence to be true, you have to have something like this: A like B, B like B, and then C like C. Okay. So, oh, sorry, not C, like C, so like B. So for the first one to be true, you have to have everyone like someone. It doesn't have to be the same person, but everyone has to like someone, right? The second situation, it will be true if everyone likes someone, then that they are the same. Okay, maybe A can like C as well, but as long as everyone like the same person, or there is one person that everyone likes, uh, this will be true. Okay, so which means that this sentence is not the same. Okay, the sentence is not the same. Okay, so which means that you cannot just swap for all and for some and for some and for all. Okay. Any question for this one? Okay. Now, finding the truth value of the multiple quantifier statement. This one a little bit difficult. Okay, but I think it's well, if you read it carefully, you may probably get it. For example, uh, let's see some example. For any positive integer, there is a smaller positive integer. Okay. For any positive integer, there is a smaller positive integer. Is this sentence true or false? For any positive integer, there is a smaller positive integer. It is, well, because this one say that for any positive integer, which means that any or all positive integer, there must be a smaller positive integer. Okay. So this sentence will be true if all the positive integer has a smaller positive integer. And it will be false if you can find one positive integer that has no smaller positive integer, right? So as you can see that these, for this sentence, um, one example that will make this sentence false is that you can have a number one. Oh, actually, I wrote it here. So because when x is one, right, one is positive integer, right, but there is no smaller positive integer than one, right? Well, we know that another integer that is less than one is zero. A zero is not positive, right? So there is no positive integer that is less than one. So this one is false. Okay. I'm just gonna skip this one because I don't think. Well, this one is similar to the negation of one single quantifier statement. Okay, but this one you have two multiple or at least two quantifier statements. Okay, so this one is that saying that the negation of this one is equivalent to this one. Okay, so you have for all, for some p of xy, which will be equivalent to for all, you just switch to for some, and then for some, you just switch to all, and then p of xy, you just put the negation of pxy. Okay. Similarly, if you have for some first for all, p of xy, you can say have for all, and then for some, and then negation of pxy. Okay. All right. So for example, okay. So for example, let's find the multiple quantifier statements of the following sentence. Okay, let's say that you have the symbol p of xy, say x love y. Okay, can you translate the following sentence into the quantifier statement? Okay, so you have everybody loves Tom. Everybody loves Tom. So you can see that, oh, this one has two people. I mean, two people means like everybody, that's one, and Tom is the second person. So for everyone, it's a variable because it doesn't tell you who it is. So you have to use a quantifier. So because it's everyone, so you use for all, right? So this one you can say X to be for all, X, okay, PX, Tom, which means that every X love Tom, right? So the second one, everybody love somebody, okay? So there are two persons. Okay, the first person is everybody. The second person is somebody. Let's say the first person, let's say we use X for the first person. The second person, we use Y. Okay. So because the first one, everybody, we use for all because it's everybody. And we use for y, we use somebody, we use for all. I mean the axis, right? So that it will be for all x, the x is y, okay, that's y. Okay. The next sentence would be there is somebody whom somebody loves. First, you identify how many people in this sentence, right? You can see, oh, that's two, somebody and somebody. Let's say the first one, somebody is x. The second, somebody is y. Because it's somebody, you can have the axis. So the axis x, the axis y, p of yx. Notice that I put p of yx because this one saying that is somebody whom somebody loves. So x is loved by y, right? X is loved by y. That's why I put pyx, okay? Because of the whom. And the last slide, which I will just do the first one. Okay, this one is a little bit difficult, but I'm just gonna skip this slide. Okay, and then we're not gonna do the rule of inference. Okay. This one, okay. I think this is it. Okay. Okay. So that's all for the predicate logic. Any questions? So we're not gonna do from the page 23. Okay, so it's a little bit. We're not gonna use it, so I'm not gonna. I think we can skip it. Okay. Any question? Nope. Okay. We should start the second. Sorry. Okay. We should start the second lecture. Oh, wow. So the next topic we'll discuss on the lecture number 8. Oh, it's actually number 7. Oh, I actually 7. Okay. We'll discuss about the theory of probability. Okay. The theory of probability, which I split it into parts. The first one is like a basic of the probability, and the second part is the more advanced probability. Okay. So I assume that everyone has learned some kind of probability before. Okay. So let's see what is a probability and why are we why I named this one basic accounting. Okay. Well, I named this lecture basic accounting because in order to find the probability, you have to be able to count what you want to know. Okay. So basically, we're not gonna count. So, sorry, so we're not gonna count 1, 2, 3, 4, 5. Like that. You just need to learn how to count. Okay. Um, I think I updated the wrong lecture, but that's okay. Okay. So in this lecture, we will learn how to count. Okay. Not what to count. Okay. I mean, we learn what to count, not how to count. Okay? Everyone assume everyone can count 1, 2, 3, 4, 5, but not everyone can count like what to count and what's not to count. Okay. For example, when you tossing 2 coins, okay, tossing 2 coins, 2 Thai baht coins, okay, and you want to know how many. Can I just update the slide a little bit? I think I used the wrong one, but yeah, นะครับ 1 second. I think I used the wrong. I upload the wrong one. Well, not the wrong one, the correct one, but I upload the one that for presentation. Okay. นะครับ 1 minute. Okay, let me just get rid of this one. Capturing. Oops. Okay, this is the correct one.นะครับ Probably everyone know how to I mean toss a coin, right? Okay, the example is this. Let's say that you want to toss 2 coins, okay, a Thai baht coin, let's say. So the possible outcome of tossing one coin is head or tail, right? Let's say that I will use a letter H for head and a letter T for tail, okay? So if you want to toss 2 coins, the possible outcome will be like this, right? H will means head, right? And then you have HT, head, tail, right? And then you have TH, tail head, and then you have TT, tail, right? That's all the possible outcome, okay? Now, if the question is how many times both coins are head, okay? How many times both coins are head? So how many times both coins are head? Okay. So as you can see, if we have HH, HT, TH, TT, there's only one outcome, right? That have both times are head, right? Okay. So because the coins are like not rigged, right? So the outcome is equally likely. Equally likely means that it's like random. So the outcome would be equally head or tail, right? We have a word that called a sample space. A sample space is that it's a set of all possible outcomes, right? So we can say that S, or the set of sample space, is a set of HH, HT, TH, of TT. Okay, that's the sample space. Okay, and we can say that an event is something that we're interested in. Okay, so in this case, an event that we're interested in is that all head, right? So both coins are head. Okay, so this is what we're interested in. Okay, so the probability of the events, okay, can be calculated using that probability of E is equal to the cardinality of set E, or the size of set E, divided by the size of set S. Okay, so in this case, the size of set E is 1, and the size of set S is 4. So there is 0.25, right? Or we can say that 25% of chance of getting both coins are head, right? Okay. Now, what about a card? Everyone, so what about cards? I assume everyone know how to play cards. Yes. So, so, so let's see. Well, in case not everyone know how to play cards, so a deck of cards contains 52 cards. Okay. In these 52 cards, the cards are divided into 4 suits. Okay. Uh, 2 suit or 4 suits or two color suits. Okay, 2 color suit are red suits and black suits. Okay, red suit including diamond suit, heart suit, um, club suit, and spade suit. Okay, so each suit contains 13 cards, including number 2, 3, 4, 5, 6, 7, 8, 9, 10, J, which we call it Jack, Q, which we call it Queen, and K, which we call it King, and A, which we call it Ace. Okay. And sometimes we call J, Jack, Queen, King are called face card, because I don't know, if you have a deck of cards, you can look at it and then it has a face on the card. Okay. So let's say that you have a deck of cards. What is the, let's say that you truly mixed, okay, and then you pick 1 card from the deck, okay, 1 card from the deck. What is the sample space of the outcome? Okay, well, the sample space of the outcome is what? Because we pick 1 card, okay, we have 52 cards, so the sample space is actually, S would be something like, I don't know, 1, uh, oh no, not 1, sorry, 2 hard, 2, um, still my right drawing, 2 hard, 2 space, 2, something like that. Okay, so you have 52 cards. So that's the sample space is 52 cards, and the event that we interested in. Okay, that we interested in. What is the event that the chosen card is a black face card? Okay, so the black face card, including Jack. Well, it has to be face card, which means that Jack, Queen, King, and it has to be black color. Okay, so you have, what is it called? Club, Jack club, Queen club, and King club, Jack spade, Queen spade, and King spade. Right. So you have the number of the event equal to 6. So the probability of choosing 1 card at random, and then you get the black face card is equal to 6 divided by 52, which will equal to about 11.5%. Okay. Okay. So basically, let me just say, in probability, you only have to know 2 things. Okay, one formula, which is the probability of anything that you're interested in will be equal to the number of the the thing that we're interested in divided by the number of all the possible outcomes. This is the only probable, the only formula that you need to know. Now the hard part is this. Okay, the example that we just seen are easy to find the number of E and the number of S. Okay. But sometimes it's very difficult to find. For example, let's say that what is the probability of winning the 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 first prize lottery, let's say. Um, okay. What is the probability of winning the first prize of the buying the lottery? Oh, that one's not hard. Well, let's say you want to find this. Sometimes hard, right? So how many first prize lottery you can win? How many lottery you buy? How many possible lottery are being sold, right? So all this is kind of hard. So in this slide, we will learn how to do all this, how to count, what to count, what not to count, how to count quickly. Okay. And then finally it will come down to this formula. Okay. The number of events divided by the number of all possible outcomes. Okay. Any questions so far? Okay. So just to warm you up, I have a quizzy. Let's stop this one. เดี๋ยวเรามาทำควิสซี่กันนะครับง่ายๆเนาะ Let me just shareโอเคเดี๋ยวเรามาจอยกันนะครับโอเคนะครับ everyone can join now on the joinmyquiz.com and then you can enter the game code 342556. Okay, I'll just gonna wait for 5 minutes for everyone to join. Okay ครับ25 people join. Remember, you have a participation point mark when you join. Okay, either you join and then, well, I mean, regardless of how you do on the on the quiz. So 27. Let's see how many people today. 40. Ooh. All right, let's wait for 1 more minute.
ดี๋ยวนะครับทำไมพุ้ยเป็นแปลกๆอะครับ
อาจารย์ไม่ได้เปิดไมค์หรือเปล่าครับ
โอเคได้ยินไหมครับขออภัยครับเข้าผิดอันเข้าอันใหม่ครับอันนี้เนาะ259000ครับ259000นะครับขอบน่าชมกันนะครับ32 คนมากกว่าเดิมอีกนะเอามาเริ่มกันนะครับเดี๋ยวนะ How many outcomes are in the sample space for tossing coin one coin โอเคนะครับโอเค so the leaderboard and okay well how many outcomes are in a sample space right we talk about the earliest slide we talk about outcomes right outcome is the result of throwing one coin okay they're saying that how many outcomes are in a sample space sample space is a set of all possible outcomes right so the one's asking how many possible outcome there will be okay so as you can remember tossing one coin there are only two possible outcomes right either it's head or either it's tail right so well most of you got it correct some of you got it four not sure how come how the answer is four well maybe you misunderstood the question but okay next one
Okay, so this one asking which of the following are possible sample space for tossing two coins, right? This one is actually in the slide earlier. Okay, I give you a hint that there may be more than one correct answer. Okay, so basically two coins, right? You have one coin and then the second coin, if you have H as the head, T as the tail, you have HH, That's probably the original answer. But of course, in the set, you can, there is no order. There's no correct order. You can order it as TT, as well. So all the answers are correct. Okay. Okay, so now three coins, right? So three coins, if you have the H as the head and T as the tail, we can have something like H mean that the first coin is head, the second coin is head, the third coin is head, right? So you have H, T, Basically, you have possible outcome of eight, okay? Because you can have two possible outcome for one coin, another two for the second coin, and then another two for the third coin. So all possible outcome is just basically 2 to the power of 3, which is 8, right? If you list it, the fourth the answer is the most correct one, right? The third one, which 11 people answer, I think you missed some, okay? Right, you missed some, like I think HTH. Oh, yeah, you missed HTH. Yeah, some. Just this one, not all the possible outcome. Yeah. Just gonna go a bit quicker now because we have 20 questions. So this is the hard one. If you answered wrong, don't worry. This is a hard one. Oh, so leaderboard. Ooh, okay. Swap up the leader. Okay, so it say that you if you have a paper marked number 1, 2, 3, 4, 5, okay, and then you put it in the box, and then you're mixing up, and then I think this one not clear, like how do you take two slip out, okay, basically you take one slip out and then put one, the one just took out back in, and then you take another one out. Okay, so how many possible outcome are there? Okay, so basically you can have 5 possible outcome for the first take, for the first taking out, and the another 5 possible outcome for the second taking out, right? Because the first draw you can have either 1, 2, 3, 4, or 5, right? The second draw you can also have 1, 2, 3, 4, 5. The question is not clear, right? Because we're putting the slip back after we draw the first one. Okay, so the correct answer would be 25, right? Because 5 for the first one, 5 for the second draw. So 5 times 5, 25. We will learn how to calculate this, and then the technique of how to use, like, should I multiply, should I add them? Okay, but I'm surprised 20 of you got it correctly. Well done. Ooh, swap of the leader again. Okay. So this one, you have three questions, right? It say that you have a three question, two true or false. Okay. Then the student answer all three questions. What is the probability that he gets all three correct? Okay. So imagine three questions, right? Each question have two answer, true or false, right? So how many possible outcome he can answer? Well, he can answer, you can say, well, he can answer true, 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 right? True, true, false, true, false, true, true, false, false. Basically, there are how many outcome? Eight, right? You can try to list it, right? True, false, and true, 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 false, true, 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 false, right? If I don't know if you remember the truth table, how many rows? Okay, if there are two possible outcome for each rows, they are 2 to the power of 3. Right? So the bottom one is 8. You can see that. And it say that what is the possibility that he get it all correct. So we don't know what the correct answer is. It might be true, true, true. It might be true, true, false, but we not really care because it say that what's the probability he get all correct, which is only one possible outcome. Okay, we don't know what it is. It could be all true or all false. Okay, so the answer of this one is 1/8. Okay, 1/8. 1/3. I can see some of you answer 1/3 because you say that, oh, okay, three questions, right? But it's actually 1/8. Okay. Okay, นะครับ this one the question is you give the answer to the probability problem as 6/5. The teacher mark it wrong. Why? Okay. Well, I haven't gone through the probability properties. Basically, the probability is at maximum as 1. Okay, which means that it's 100. Okay, so the probability can never be greater than 1. 6/5 is greater than 1, so which is definitely wrong. Okay, the answer should have been 5 or 6. That's not correct. Not writing ampersand, that's not correct. More than 1, yes, that's correct. And then not written as a decimal, that's not correct. So most of you got it correct. Yeah, more than 1. Probability never be greater than 1. Okay, but if you convert it into percent, it never be greater than 100%. You can't say 200%, 1000%. No, that's not real. Okay, next one. Thank you.
Can you put it back?
Yeah.
But it's wet.
We can wait. Okay. The second one, this question is saying that which of these cannot be considered probability of an outcome? There are more, could be more than one answer, right? So the first one is 1/3. Yes, that's definitely fine. Minus 1/5. The negative probability is not real, okay? 0.8, that's fine. 1 is okay, but 112% is not correct. Okay, so this one, most of you got it correctly. Well done. Next one. So this one is saying that roll a die, roll a die one time. Find the probability of rolling a 4. Okay. So everyone know die, right? A dice or a die. A die has 6 faces. So number 1 to number 6, right? So the probability of rolling a 4 is 1 divided by all the possible outcome, which is 1, 2, 3, 4, 5, 6. So the answer is 1/6. Okay. Most of you answered correctly. Thank you. 1/6, yes. So the next one. Everyone know about even number, right? Even number. Okay, so this one is saying that roll a die one time. Find probability of rolling an even number. Okay, so rolling a die, all the outcome is 6, right? You can roll 1, 2, 3, 4, 5, 6. But the event that we're interested in that is rolling the even number. So even number is the 2, 4, and then 6, right? So the number of rolling even number is 3 divided by all the number of all possible outcome, which is 6. So 3 divided by 6. So the answer is 1/2, right? Yes, most of you got it correct. 1/3. 1/3. Yeah, 1/3 is not correct. So 1/2, right? You 3/6. Next one. So this one is saying that this is a kind of a trick question. Roll a die one time, find the probability of a number less than 7. Well, basically everything is less than number 7, right? So basically this one is 6 divided by 6, right? Because all the possible outcome is 6 divided on top will be the number of all possible row that can less than 7, which also 6. So 6 divided by 6 is 1. So this one answer to, most of you got it correct. 1 over 6. This one not 1 over 6. Okay.โอเคนะครับข้อนี้นะครับ this one roll a die one time find a number greater than 3 or odd. Okay, so you have to start counting now. So the probability is the bottom letter, I mean the bottom number, which is the number of all possible outcome, is always 6, right? But the top one of event that we're interested in this case is a number of the number of greater than 3 or odd, which is, what is it? Greater than 3. Greater than 3 is 4, 5, 6, right? Or odd. Odd is 1, 3, 5, right? So together, what number do we have? So we have 1, 3, 5, and then 4, 5, 6. Oh, so we have 1, 3, 4, 5, 6. So it's actually 5 of them, right? Divided by 6. Okay. 1 over 2. 1 over 2, I'm not sure. 1 over 2. No, it's actually 5 over 6, right? We have 1, 2, we don't count. 3, yes. 4, 5, and then 6. Yeah, 5 over 6. Ooh. เดี๋ยวนะครับ ต่อไปนะครับข้อนี้นะครับเนาะถามว่า draw one card from a standard deck วันนี้ข้อนี้ this one you have to understand a deck of cards. Okay, so draw one card from a standard deck. Okay, find a card that is an ace. Okay, so basically this one, the number of all possible outcome is 52, right? Okay, but now the number of event that you can draw ace. How many ace in a stack? 4 ace. Okay, ace as of spades, ace of club, ace of diamond, ace of hearts. Okay, 4 ace. So it's 4 divided by 52, which is 1 over 13. Okay, well done for those of you who got it correctly. Next one. Okay. So this one asking draw one card from a standard deck, 5p of diamond. Okay. So this one, oh, most of you got it correctly. Now you understand. I think you understand the question now. So how many cards are in diamonds? 13, right? 13. Well, oh, this one answer is not, it's in percent, right? So 1/4 of the cards are diamonds. So 25%. Very good. You have 15 minutes. Okay. Sorry, I wasn't talking to you earlier. Okay. So this one, it's a draw one card from standard deck, 5p of ace of diamonds. Ooh. So p of ace of diamonds. So I think you need to go back and then learn about card a little bit. Okay. So this one, again, the number of possible outcome is 52. Now the question is, what is the number of ace of diamonds? How many ace of diamonds are there in the card? It's only one, okay? One of them, ace of diamonds. There are 4 ace of cards, okay? But there are one ace of diamonds. So this one is 1/52. That's the correct answer. Well done. 17 of you. Okay, no, so this one, draw one card from standard deck of card, 5p probability of 4 or club. Ooh. So 4 or club, okay. So again, the number of all possible cards are 52, but you have to find how many cards that have number 4 or club, okay. I think next week we will find this number quickly, but let's start. Let's do a little bit of counting. So number of cards that has number 4, there are 13 of them, right? You have oh no, not 13 of them. 4. There are 4 of them. So 4. There are 4 cards of number 4. Okay. However, there are 13 of the cards that are club, right? Because each suit has 13 cards. So 13 of club and 4 of number 4. However, we can just add 13 plus 4 because there are some repetition in that, right? Because number 4 of club, both in the same 4 and club, right? So you have to add 13 plus 4, which you get 17, and then minus 1, which is the repeat of the 4 and the club, right? So you get 17 plus 3, 13 plus 4, 17 minus 1, 16. So the answer is 16 divided by 52. So once you factor out, you get 4 divided by 13. Well done. This one, this is a hard one. Next one.
Time's up.
Okay.
I've only done 3 yet.
Okay. Okay, this one, draw one card from standard deck, P of black and a 10. Oh, this one, is it the same? So, oh, black. So again, how many cards are black and 10? So how many are black? So half of them are black, right? So that's 26. How many are 10? So 10, you have 4 of number 10 cards, right? 4 of number 10. So, but there are 2 cards that also 10s and then black. So you count twice, right? Black's 26 and 4 of 10, right? So you can add 26 plus 4, that's 30, but you have to subtract 2 out because the 2 is counted both sides, right? Black and 10. So you get 30 minus 2 is 28. So 28 divided by 52. I do it correctly. 26. 26 plus 2. Oh, 20. Oh, yeah. So 1 over 26. Oh, yeah. Oh, next one. Oh. Now this one,นะครับ. This one, roll a pair of dice. Okay. P rolling doubles. Rolling doubles mean what does it mean? This one hard one. Which means that you roll two dice, right? Roll doubles means you roll the same number of the first dice and the second dice. Okay. First, you have to find all the possible outcome first. What is the possible outcome? So the first die, you can roll 1 to 6, right? The second one, you can also roll up to 1 to 6, right? So all the possible outcome is what? 6 times 6, that is the 36, right? However, what is the number of probability that you can roll doubles? You can have what? If the first one is rolling 1, the second one you have to roll the same number. So 1, 1, 2, 2, 3, 3. So you have 6. So the answer would be 6 divided by 36. So that's 1 over 6. Okay. All right. 13 of you got it correctly. All right. 3 more questions. Oh, I didn't think it was going to take this long. And this one is kind of difficult because you want to find the probability of the sum of 2 dice that is greater than 9. I want to have a piece of paper. But basically, the possible outcome again is 36, right? Because 6 for the first dice and another 6 for the second dice. So it's like 36 possible outcome. Now, you want to find the dice that, how many that you can roll such that the sum of the first and the second is greater than 6. I mean, greater than 9. So if you, let's say that the first one you get 1. So no matter what the second one will get, you will be less, the sum will be always less than 9, right? Because 1 plus 1, 1 plus 2, 1 plus 3, now less than 9. So for the if the first one is 2, you get 1, no, still less than 9. If the first one you get 3 plus 1, no, 3 plus 2, 3 plus 4, 3 plus 5, 3 plus 6, still less than 9, which means that the first dice has to be greater than 4, right? For if the first one is 4, the second one has to be the first one is 4, the second one has to be 6, so that's 1. The first one is 5, the second one can be 5 and 6, so that's 3 in total. The first one is 6, the second one can be 4, 5, and 6. So that's 6 in total, divided by 36, so that's 1 over 6. Well done, 10 of you. And I think that's the last one. This one really difficult.
อาจารย์ลืมเปิดไมค์ค่ะ
So again, this one, you roll 2 dice, okay? You want to find the probability of both dice, the sum of both dice is 7 or 11, okay? So 7, you can have like, if the first one is 1, you can kind of like see, like if the first one is 1, the second one has to be 6, right? If the first one is 2, the second one has to be 5. So 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and then 6, 1. So you have 6. What about 11? 11 you get, if the first one 1, nope, the second one is 2. So 11 would be 5, 6, and then 6, 5. So you get how many? 8 of them. 8 divided by 36. So that's how many? About 22%. Let me just calculate quickly. 8 divided by 36. Yeah, that's what 22%. Okay, that's kind of hard, but okay. The last one. Sorry. Okay, so rolling a dice, the 5 sum is 5. Okay, so again, the all the possible outcome is 36, but the sum is 5. So if the first one is 1, you get 1, 4, 2, 3, 3, 2, 3, 2. The first 3, the second 2, this first 4, the second 1. That's it. Okay. 1, 4, 3, 2, 2, 3. Oh no, 1, 1, 4, 2, 3, 3, 2, and then 4, 1. Yeah, that's it. 4 divided by 36, basically, right? 4 divided by 36, that is 11%. So the answer is 11%, okay? And that's all the question. Just about time. Let's see the winner for today, which isคุณธีรเดชนะครับคุณวรวัฒน์เนาะแล้วก็คุณพานุกันนะครับjust to quickly see wow. โอเคนะครับเนาะ So that's kind of like the basic idea of what we're gonna do. We're gonna do a lot of dice, a lot of cards. Okay, we're gonna maybe the reason we use a lot of dice, a lot of cards because it's easier to understand. But you can always apply into something else. Okay, next week we're gonna see some application in the real world. Okay, we're gonna play. I don't know if you have and any of you have played like a poker or like a blackjack cards. Okay, we're gonna maybe learn how to play those games and then how to count and then how to see the probability of how to play all those games. Okay, and then we're gonna dive into what if you buy a lottery. Will you be able to make profit out of buying a lottery? How would you buy? How you make a profit of buying a lottery from a real world example? Okay, so it's kind of a fun topic, and you can apply to many things that you can. Everything that you make decision, of course, you have to calculate the probability of everything, right? The probability of, well, if this afternoon the probability of the rain is gonna come, if you should carry an umbrella or something like that. So that's how we're gonna do for the, I think, next week. Okay. Any question for today? Okay, if no question for today, thank you. This I'll see you all next week.